Thank you for everyone for joining for this week's Space at VT seminar, which we have recently. Was it master's or PhD defense? It wasn't clear to me.
It's my PhD defense.
Okay, that's what I thought, but it wasn't specified. So I guess it's
that's right.
Is it too premature to call you Dr. Augustine or?
Oh well, I mean my degree is gonna be awarded in December, right? I think they awarded at the end of the semester, but they're gonna issue me a letter that shows that thanks, Len. That shows that like I've fulfilled all the requirements. So my committee actually called me doctor, but I guess I don't have it yet. So
yeah, they can call you doctor, but you can't put that on a resume because it's not official. But
yeah, it's not official. Yeah. So just Augustine.
Okay. Well, thank you, Augustine, for putting together some slides, and certainly looking forward to this. I've known about kind of this work, especially with using like I was saying, a high power. I think is putting it modest, considering ionospheric heater. But very interested to hear that. Just wanted a quick note. Sorry about last week on things kind of running away. That was our regular scheduled. We'll get back on schedule a little bit more next week from with a seminar, I believe, from Dr. Leonard, or he goes by Lenny Smith, with the title here of Predictability and Probabilistic Support for Decision Making, Questions from AI, Energy Supply, and the NFL. So we'll get some more. I think he was saying that the might change a little bit, but I'll certainly get that information up here in the next week and send it around. But otherwise, yeah, thanks for joining us. And without further ado, we'll turn it over to Dr. Sorry, we'll say just Augustine.
Augustine.
On a talk titled with SEEs. I like that. The simulated electromagnetic emission, second harmonic generation during high power HF radio wave ionosphere interaction. So stop here and I'll let you take on over.
Okay. Let me see. Well, thanks a lot for joining us this afternoon, and thanks a lot for inviting me to give this talk, Kevin. Let me just a second. Let me try to figure out things over here. Slideshow. Okay, so the title of this talk, as Kevin already said, is Second Harmonic Generation Stimulated Electromagnetic Emissions During High Power, High Frequency Radio Wave Interaction with the Ionosphere. So I know this is a handful, but I'm going to break it down so that we are all on the same page as to what this long title means. So most of my work was supported by the NSF and the interdisciplinary program and remote sensing. So again, most of us in this talk are all engineers. So we appreciate the fact that like scientific and mathematical theory, no matter how elegant it is, it means very little to us if we cannot design experiments to prove and validate these theories, and more importantly, put them to practical use. So again, so this topic is just like it's gonna display something in the same light. It's gonna be mostly based on experiments. So I'm gonna introduce you to the bigger general area under which this topic falls under. Then I'm going to try to break down the title, like define everything in this long title, then give you just a basic picture of the physics involved. And I would show some past work that has been done, and I'll highlight the gaps in those past works. And I would then highlight how my work with Dr. Skills has sought to close some of those gaps in past research. So the bigger general area under whose remit my topic falls under is called ionospheric modification. So this simply refers to any action that causes the properties of a local region of the ionosphere like to vary significantly or deviate significantly from the properties of the background or surrounding ionosphere. And there are several sources of ionospheric modification. You could have natural sources like earthquakes or volcanoes, and you could have man-made sources like high explosives and nuclear explosives. So earthquakes, nuclear explosives, and high explosives, all these generate mechanical waves that couple from the lower atmosphere into the ionosphere and can change the physics of the ionosphere. And there are other processes. There are times where we intentionally seed the ionosphere with plasma plumes or gases. And the purpose of this is to understand how plasma diffuses in the ionosphere. Or there are times you could just inject a highly ionizable gas into the ionosphere to study their photochemistry. Okay, so the first modification by means of radio waves was unintentional, right? So in 1933, listeners in Holland who were listening to a Swiss radio station realized that the radio transmissions were modulated by modulations from a very strong radio station located in Luxembourg. So the kind of experiments I perform are called ionospheric heating, and this is the deliberate injection of high power radio waves, usually in the HF frequency range, into the ionosphere. Right, so I have this cartoon on the left-hand side where I show these high power transmitters injecting a radio wave vertically up to interact with the ionosphere. And several processes occur like through this action. One of the first processes is that the radio wave can generate irregularities or striations, which are generally layers of plasma depletions aligned along the geomagnetic fold. You can also couple your electromagnetic wave into natural modes of like the plasma. There are waves called, most of us are familiar with EM waves, which are transverse waves. But in the plasma, you can have electrostatic waves, which are longitudinal waves. And another thing that can occur is that you can increase the temperature of the electrons in the ionosphere. And this is why these experiments are called ionospheric heating experiments. Also, you could accelerate electrons, and these electrons could then impact on neutral atoms or molecules, excite those atoms and molecules, and when they de-excite, they give off air glow. And also, you could generate secondary radiation called stimulated electromagnetic emission. So I'm going to go more into detail of this later. And usually, like when we perform these experiments, we have other instruments or systems making other measurements. So you could have a coherence backscatter radar like SuperDAN that would measure small scale irregularities and their drift velocities. You could have ground optics. You could have GPS receivers to measure TEC and scintillation. So now I'm gonna start breaking down like the topic of the title of this talk. So stimulated electromagnetic emissions refer to secondary emissions produced during ionospheric heating experiments. And these were first theoretically predicted in 1978, but the first experimental observations were made in Norway like 4 years later. So the production of simulated electromagnetic emissions around 2 times the transmit or pump frequency is known as second harmonic generation. So I have a typical experimental setup over here of the experiments I perform. So on the left-hand side of your screen below, we have a high power transmit station, in this case, HAP, the high frequency or active auroral research program facility in Alaska. That's where I usually perform my experiments at. Sending out a clean radio wave, like a very narrow band radio wave centered around the transmit frequency, which are represented by omega naught, which interacts with the ionosphere, typically the F region ionosphere. And the interaction is strongest between where the radio wave frequency equal the plasma frequency and a couple of kilometers below there where the radio wave frequency equal the upper hybrid frequency. So this upper hybrid frequency is another is a characteristic frequency of a magnetized plasma, and it's basically equal to the square root of this, the square root of the square of this frequency I have here, the electron plasma frequency, and the square of another frequency which characterizes the rate at which the ionospheric plasma electrons circle around the geomagnetic field. Now, if you set up a remote station, and in my case, it's about 15 kilometers from HAP, instead of receiving this clean radio signal, we have all these other emissions and broadening, which I've tried to indicate with arrows over here. So these are called simulated electromagnetic emissions. And now when these emissions occur around 2 times the pump frequency, this process is called second harmonic generation. I hope I've not lost anyone so far. Okay, so the physical mechanism, I'm now going to talk about like how these SEEs are produced. So these SEEs are produced via parametric instabilities. So in a parametric instability, our pump wave, the incident wave from the transmit station, decays into other waves. And just I'm going to talk about just a 3-way decay process wherein the pump, the transmit wave, which I indicate with an index 0 over here, decays into 2 waves. One wave is high frequency and the other one is low frequency. The high frequency wave can be a transverse wave, just like the pump wave, or it can be an electrostatic wave, and a low frequency wave is always electrostatic. So the waves in the parametric instability must conserve energy, which simply means that the pump frequency must equal to the sum of the frequencies of the decay products. And this process must also conserve momentum, which simply means that the wave vector of the incident wave has to equal the sum of the wave vectors of the decay products. So I try to illustrate it with a cartoon over here where I indicate the pump frequency by this emission line over here. And I show the high frequency decay product by this emission line over here at omega 1. So over here, if we look at this equation, one wave which is missing in this frequency is the low frequency wave, which is represented by index 2. But by simply looking at this equation, we realize that the shifts between this emission line and the emission line at the pump contains the frequency omega 2. So now once we know omega 2, we can now infer what kind of parametric instability is occurring. We can identify the waves involved in the parametric instability. And once we know the wave omega 2, we can now write its dispersion relationship, which simply would relate omega 2 to K2 and the properties of the ionosphere like electron temperature, ion acoustic velocity, etc. So this is where the value of SEEs come in. Just by measuring this simple shift, if we can now write the dispersion, it's more complicated than that, but it just suffice to say that we can write the dispersion relationship for the low frequency electrostatic wave. And from it, we can infer the properties of the that region of the ionosphere where we've injected the radio wave into. So this is where I perform all my experiments. So this is HAP, is located in Gacona, Alaska, and is currently managed by the University of Alaska Fairbanks. And it has 4 diesel engines that power like transmitters, which are located in these shelters. And this big array you see over here is just called the Ionospheric Research Instrument. And just from the size of this, you would realize that this is a high gain facility, like a high gain facility. It has 180 dipoles on a footprint of 33 acres. And the peak transmit power is 3.6 megawatts, but this is high gain. So you're talking about an ERP in excess of like several gigawatts. So you can tilt the beam from vertical out to about 30 degrees. You can, during experiments, we've made coordinated measurements with the Superdome facility in Alaska. It has several other diagnostic tools nearby to make other measurements. This is the second facility like closest to us. So I guess we've all seen this before. This is the Arecibo Dish. And on this dish somewhere, there are HF dipoles and there's a sub reflector. And this system is just, it's designed for just vertical transmission for heating experiments, and it's co-located with the most powerful incoherent scatter radar facility in the world. But unfortunately, just this year, these ropes holding this platform snapped, and this thing fell and damaged the dish. So it's expected that it's going to take a couple of months to get this operational again. And I'm going to step through these very fast. This another facility called Sura in Russia. The good thing about this is that you can squint the beam up to 40 degrees from the vertical. And actually the first intentional ionospheric heating experiments were performed at a facility just about 30 kilometers from where this facility currently is at. And this is another facility in Norway, Tromsø, near Tromsø, Norway. And Virginia Tech has performed their experiments over here in the past too. It's co-located with an ISR, unlike HAP. And it's used to have, currently transmits from 3.8 to 8 megahertz, but it used to have the ability to transmit in a lower frequency range, but that got damaged. So just to like sanitize the presentation, there are lots of definitions and categorizations of SEs in this talk. So I'm going to try to give the definitions over here, and please feel free to stop me if I lose you anywhere. So the first row over here represents the pump wave channel. So omega naught is the pump wave frequency. And the second row represents the second harmonic channel. That's 2 times the pump wave frequency. Well, so all stimulated electromagnetic emissions which exist outside plus and minus 1 kilohertz of the pump wave frequency, we are going to refer to them as pump wave wideband stimulated electromagnetic emissions. And all SEEs which exist within plus and minus 1 kilohertz of the pump wave frequency, we are going to call them pump wave narrowband stimulated electromagnetic emissions. Now, when we come to the second harmonic channel, again, just the same kind of definition. Emissions within plus and minus 1 kilohertz of twice the pump wave frequency, we're going to call them second harmonic narrowband SEEs, and those outside this frequency range, we are going to call them second harmonic wideband SEEs. So the first experimental observation of SEEs was done in were made in Norway, and I show a capture from these first observations. So they sent out a clean radio signal, and yet at the received side, they saw all this broadening, the broadening over here, and it's asymmetric. And the only conclusion they could give was that this was of ionospheric origin. Again, so in the early days of these experiments, they gave names to like these structures, which were kind of phenomenological, like just names that describe how they look like. So there's another structure called the downshifted maximum, and there's another one called the downshifted peak. And again, all these emissions, if you look down over here on the abscissa, the frequency is in kilohertz. So all these wideband SEEs, they exist outside plus and 1 kilohertz of the pump wave frequency. And there are several reasons for this, DSP technology was not as advanced as it currently is. So they could only make measurements which were as good as the resolution of the spectrum analyzers and receivers they had. And also the SEEs that exist very close into the pump wave frequency actually require very high powers. And we didn't have high transmit powers available at those at the ionospheric heating facilities at that time. So this structure over here, which is also called a DM, is downshifted by 8 kilohertz and is indicative of these striations. So if you see a DM, then more than likely your pump wave is generating these structures in your ionospheric plasma. And so just at the dawn of the century, because of improved receiver technology and high power availability at the various ionospheric heating facilities, people started making observations of SEEs very close to the pump wave frequency. And again, if you look at the x-axis over here, the units are in hertz. Okay. The first measurement very close to the pump wave frequency was made at HAP for a transmit beam oriented along the local direction of the geomagnetic field, right? So they observed these SE lines at about like 20 hertz downshifted from the pump wave frequency. And a year later, other experiments revealed that, okay, like when you start tilting the beam away from the direction of the geomagnetic field, you pick up another SEE line, which is at 50 hertz below the pump wave frequency. And this 50 hertz is the O+ ion cyclotron frequency. So, and we know that O+ is the dominant ion in the F, like in the F region of the ionosphere near the reflection region. So this just shows again the value of SEEs, that we can use them as ion mass spectrometers to detect what ions are in different regions of the ionosphere. Later experiments also show that on occasion, we could measure SEE lines, several SEE lines, and all these are spaced by the O plus ion gyro frequency. So Virginia Tech in the past has done a lot of contribution to these ion cyclotron harmonic SE structures. So the first measurement, it was in 2011, and they measured these they observed these SE lines spaced by the H plus ion cyclotron frequency. And it happened that these experiments were performed during a storm time event. So these lines just represent the H plus ions which precipitated into the Earth-region ionosphere due to like the storm time event or whatever was occurring. And I'm gonna jump to this last one just for want of time. And again, SEEs were observed that were downshifted by the O plus, the sodium ion cyclotron frequency. And again, sodium, we know that we can find sodium ions in sporadic E layers and meteors. So again, you can use these SEEs to make to like detect structures such as sporadic E layers in the ionosphere. And in terms of second harmonic generation, again, I'm just gonna like show the dates. So as you can see, like the first was in 1986, they made measurements of SEEs which were downshifted by 2 kilohertz from 2 omega naught. And again, if you can remember our definitions, this is a second harmonic wideband SEE. Other people made measurements of SEEs which were spaced by harmonics of the O plus ions frequency near 2 times the pump frequency. And they also compared these with SEEs near the pump, which were outside plus and minus 1 kilohertz. And in 1998, like other researchers made measurements of SEEs, which were offset from twice the pump frequency by about 30 kilohertz. And again, these are wideband SEEs. So the interesting thing about all this research is, especially when it comes to second harmonic generation, is a lot of work has already been done in this field in laser plasma interactions. So as early as the early 1970s, they had already made measurements of SEs near twice the pump frequency, and they had developed like theories to explain the observations. So the SEEs near the twice the pump frequency proposed to be formed in a two-step process. So first, I'm just going to go through all this very fast. Like the pump wave decays into a Langmuir wave and an ion acoustic wave. Then the pump wave can either mix with a Langmuir wave, or two Langmuir waves can mix. And this is what produces emissions near twice the pump wave frequency. And the importance of second harmonic generation and laser plasma interactions is that they've used it to obtain various diagnostics of laser plasma. So for instance, so over here, 0 represents 2 times the pump frequency. And just by measuring the shift of the main peak of the emission from twice the pump frequency, you can get information about the motion of the critical layer of the plasma. And this bulge over here can be used to obtain information about turbulence in the plasma and density scale lengths and other kinds of information. So although I've gone through this very fast, but just in terms of gaps in past work, they didn't make any comparisons between narrow SEs within a narrow band of the pump frequency with SEs within a narrow band of twice the pump frequency. They never investigated effects of transmit power like beam tilt from the geomagnetic field and offset of the pump frequency from the harmonic of the electron cyclotron frequency on second harmonic generation. They didn't make any attempts to draw from the knowledge base in laser plasma interactions to interpret their results or obtain diagnostics. And moreover, they didn't do any computer simulations to try to understand how these SEs evolved under different pump power variation conditions. And the contributions of my work were just the opposite of this. So I'm just going to share, I cannot go through the entire talk because I don't know how we are doing on time now, but so I'm going to now go through details of some of the work I did. And again, this is just a short presentation. So like lots of information has been taken out. So the first work I would shows the first ever observations of narrowband SEEs within a narrowband of the second harmonic frequency observed during ionospheric heating experiments. And the purpose of our experiment was to investigate whether there are stimulated electromagnetic emissions present within a narrow band near the second harmonic of the pump wave frequency and their association, if any, with stimulated electromagnetic emissions within a narrow band of the pump wave frequency. And we made these measurements for a transmit beam aligned along the local direction of the geomagnetic field. So these are the details of the experiment we performed. So we varied the transmit frequency from 2.0 to 4.3 megahertz in 20 hertz steps. And by looking at the ionogram, the data from the ionoson, we saw that we're reflecting at an altitude of about 190 kilometers. And we can just use the IGRF model to work out what the electron cyclotron frequency is, and 3 times of that is 4.324 megahertz. So basically, we're stepping the frequency in the vicinity of 3 times the electron cyclotron frequency. And the other important detail is that we linearly increase the transmit power from 28, the transmit ERP, from 28 megawatts to the maximum available during that campaign in 45 seconds. So this is a snapshot of like some of the results we had. So the top panel represents emissions around the pump wave frequency, and the lower row represents emissions around twice the pump wave frequency. And from left to right, we are ramping up the power. So if we start from the left, at this very low power, we just see the pump emission line, we see a second harmonic emission line. Then as we continue to increase the power, we start picking up this notch over here, which is an SE line. And at the same time, we see this other notch growing up near the second harmonic, near the second harmonic of the pump frequency. And as we continue increasing the power, you can see that the amplitudes of these two lines are increasing. So again, so the inference like from this was that yes, there's an SE line near the second harmonic frequency, which is associated with an SE line near the pump wave frequency, and they have a similar power threshold. So secondly, we wanted to study the effect of varying the frequency. So again, the data is are presented in the same way. Top row represents emissions around the pump wave frequency, and the bottom rows represents shows emissions around twice the pump wave frequency. And from left to right, we are increasing the frequency towards the third harmonic of the electron gyro frequency. And the takeaway is that when the pump frequency is very close to the third harmonic or harmonic of the electron gyro frequency, we see that this emission line over here is quenched, and these emissions lines around twice the pump wave frequency is also very suppressed. So we have shown association that these two regimes of SEEs they are both suppressed around a harmonic of the pump of the electron gyro frequency, and they have a similar transmit power threshold. And this is just the same data which shows more clearly. So the red shows the intensity of the emission line around the second harmonic, and the blue shows the intensity of the emission line around the SE line around the pump frequency. And as you can see, like they follow a very similar trend, apart from the fact that getting towards the end of the cycle, there's this saturation for the emission line near twice the pump frequency that we currently don't have any explanation for. And again, you can see that when we step across frequency, the intensities of these two lines show like a very similar trend. So I'm going to jump all these points and just go to this one highlighted in red. So we used an interpretation from laser plasma diagnostics to propose that this second harmonic line was produced by a two-step process in which the pump wave decays into a Langmuir wave and an ion acoustic wave, and the Langmuir waves produced in that decay process coalesce with each other. So again, we rely on laser plasma interactions just to explain our observations, and this makes sense. We didn't see any need of trying to develop a new theory when all this has already been done in laser plasma interactions. And I'm just going to present the next set of results so that we would have time for questions. So after we made these first measurements, we wanted to study more on how these SEEs evolve under different pump power conditions. So the purpose of this next investigation was just to investigate the characteristics of all these regimes of SEEs for different pump power regimes. So what we did was that we had two experiments, and these two experiments are very similar in all details, apart from the fact that in the first experiment, we slowly increased the transmit power from a low value to the maximum available value. And in the second experiment, we kept the power at the constant available power during the entire duration of the experiment. So I'm going to show the results for the experiments in which we slowly increase the power. And this panel over here just separates like the data, the data to the left of it just represents the first 3 seconds after we turned on transmissions. And the data to the left, to the right of it represents the last few seconds of the cycle. The top row again represents emissions around the pump wave frequency. The bottom row represents emissions around twice the pump wave frequency. What I've labeled wideband again shows emissions within a wide band of both the pump wave frequency and its second harmonic. So over here for the first few seconds, we just see the emission line representing the pump, and we see the emission line representing the second harmonic we don't see anything in the wideband. But as we continue increasing the power, again, we see this SE line near the pump wave frequency. We see another SE line near twice the pump wave frequency. And we see this downshifted peak, which I talked about earlier on. But the takeaway from this is that we see growth in the SE lines near both the pump wave frequency and the second harmonic. And we should expect this, like, since we are increasing the transmit power, we expect to see growth in these SE lines. So next, for the full power experiment, again, these are the first 3 seconds in the cycle. So immediately we turn on the transmissions, we see the strong, very broad emission line near the pump wave frequency. And we see a similar broadening of the emission line near twice the pump wave frequency. But after 3 seconds, they disappear. Like, they just go off. We don't see anything. And we see the growth of this line called the downshifted peak and the downshifted maximum again. So again, we see the takeaway from here is that for very high power throughout the cycle, we see a very quick suppression of these SE lines. And so this is just a summary plot where, and we will just concentrate on the results for this full power experiment. So this yellow line represents the intensity of the SE line near the pump wave frequency. And this line in purple over here represents the intensity of the SE line near twice the pump wave frequency. And we can see that they die off within 3 seconds. And they die off before the growth. And we are just going to look at this green line. So we see that both this yellow line and this purple line, they die off before this green line starts to grow. And this green line shows the intensity of this DM over here. And why I stress on this is that this line, this DM, is associated with striations in the ionosphere, the development of these irregularities in the ionosphere. And there was a previous study that said the suppression of the SE around the pump wave and around twice the pump wave frequency was due to the creation of these striations, which block the pump wave from reaching where these other SE lines are formed. But in our case, we observed a suppression that occurred on a much faster time scale than the growth of these striations. So we wanted to understand more what causes this quick suppression and the differences in the structure of the SEEs for like very high pump power and for low pump powers. Again, for high pump power, we saw broadening of the SEE, and for low pump power, we saw just a narrow, distinct SE line. So what we decided to do was to resort to computer simulations. So here we modeled our ionosphere as a plasma in this box, and we irradiated the plasma with an EM wave from the left-hand side. And we use particle and cell simulations, which is a standard plasma simulation method. And we sampled the reflected, the total wave in this region, in this vacuum region. We also looked at the waves in the plasma. And for low power, again, we saw a very similar characteristic as in actual experiments we performed at HARP. Here we have a distinct SE line near the pump Whereas for high power, we see this broadening as we saw in our data. And we see a similar characteristic for the waves inside the plasma. So for the electrostatic wave, we just see a distinct peak, which corresponds to this. And over here, we see this broad line and even with several cascades. So, but we wanted to understand, okay, like what's causing the quick suppression of these SE lines? So what we did was that we looked inside the plasma and we realized that with very high pump powers, there were these cavities that were being created in the plasma density. Then when we zoomed into these cavities, we realized that the temperature of the electrons were very high and the electromagnetic field in these cavities was very high too. So our proposal, again, drawing upon work in laser plasma interactions, was that the pump wave expended a lot of energy in these cavities, like to heat up electrons. And because of that, there wasn't enough energy to excite the instabilities that produce these SEs. So after a very quick time, they get very suppressed. So I'm going to try to end here. There's still like a lot of work, but for want of time, I cannot present everything. But we still have like lots of open questions. One big issue is that all this interpretation we are using from laser plasma interactions doesn't, so in laser plasma interactions, they don't have a strong ambient magnetic field. And in the case of the ionosphere, it's embedded in Earth's magnetic field. So we have to adjust the theories that we've used to interpret our results to account for the fact that the magnetic field of the Earth is very important with respect to the work that we are doing. And there are still several unresolved questions as to what is the exact altitude region where these SEEs occur from. And this plasma simulation model we used is fairly simple. It's just one dimensional in space. And we need to expand this to at least like 2 dimensions in space to be able to like really study some of the effects that we want to investigate. So I would end here. Sorry for the long talk. And if anybody has questions or suggestions, I'll be more than happy to take them.
Oh yes, I was just curious as to how a person would be able to submit an experiment for this facility.
Okay, so that's a good question. So if you have money, so last time I checked, it was $5,000 per hour of experiments, and it's currently being run by the Geophysical Institute of the University of Alaska Fairbanks, and they usually have campaigns twice a year. Right, so these campaigns are usually announced, and you can, if you're very interested, you can get in touch with Professor Skills, or you can directly send an email to the Geophysical Institute to find out when the next campaign is and submit a proposal for your experiment. You have to submit details of the experiment that you want to perform so that they would see whether they can support it or not.
Now, how is the Arecibo telescope used for this?
I
just thought you had in there.
Okay. All right, so this is the main Arecibo Dish, right? So this is a case grain design, right? So So these dipoles over here, they are located somewhere on this dish. You cannot see it from this far, but these are connected to very high, like high power transmitters, right? And this is the secondary, like the sub reflector. So again, you're just sending out these waves over here. They bounce off this and they reflect over out of this like big dish. So what this dish does is that it's gonna concentrate these rays like together, right? So this is like this where this big structure gives you like the high gain. Again, so although these dipoles are connected to very high power transmitters, is this dish that is giving it like the high gain so that you can pump a lot of power into the ionosphere. Does that make?
Were the HF dipole? When were the HF dipoles added? I don't recall seeing them in 2012 when I was down there.
So again, so can you see this picture?
Yeah, I was just wondering when they were added.
This facility has gone through like lots of changes. So again, I would have to go through my notes. So they actually used to have a separate heating facility, right? And like which wasn't like, we didn't have anything to do with the dish. So this is a fairly recent. I don't know a lot about this facility, to be honest with you, but this is fairly recent. And even this design, I think they changed it a bit after the Hurricane Maria.
Okay.
So yeah.
Well, yeah, I was down there in 2012. I just don't recall seeing the dipoles when I took it.
Okay.
Under open on top. That's why I was curious.
Oh, okay. So were you able to like look really close, into the dish? Yeah.
I was up at the sub reflector. I was also down below the dish.
Oh, okay. Yeah, I've never been to this facility anyway, so yeah.
It has actually a terawatt of EIRP. I guess I just think it would seem to be a bit overpowered for ionosphere research.
No, so again, so you have you have this dipole system over here, right? And you have a gain of about like 22 dB, and this transmits just on like two different frequencies, right? So again, you wouldn't like for the HF heater, you wouldn't have like you wouldn't have terawatts level ERP. At most you have a couple of hundred megawatts ERP.
Okay.
Yeah.
So when they transmit from the, I guess from the sub reflector or from the assembly up there, it can get up to over a terawatt of EIRP.
Okay, yeah. I mean, they use this facility for different things. So, I mean, if you are talking about the gain, you can get from it, like using it as a radio telescope and other stuff. But it's a very powerful facility. So, I mean,
You use the terawatt EIRP if you're doing like radar astronomy in the solar system, or if you want
to
beam a message into for aliens to pick up.
Yeah. If you want to talk to aliens, you need that kind of ERP.
They've done that too. Just beam a message out at terawatt EIRP out there.
I was going to ask, I think maybe I missed it. A lot of these observations have just been looking at basically zenith or what's overhead. Has there been any kind of exploration of this of I think you mentioned it about these kind of relating to waves that are right from like nuclear blast or like earthquakes or something, but so doing this in a simulated sense, but maybe in some kind of bistatic arrangement where maybe you're transmitting from Arecibo or HARP and listening somewhere else.
Oh yeah, so again, these so I mean, the kind of the configuration of my experiment, although it's kind of bistatic, but we are kind of very close to the station, right? But there've been lots of coordinated measurements again. So, right, you can transmit from HAP, and you can use the Superdown facility, which is located like several hundreds of kilometers like away from like HAP to make observations of the region of the ionosphere where you are modifying. And now there've been recent experiments that the NRL has conducted where HAP is actually beaming into the ionosphere, and a Canadian satellite equipped with receivers is basically making kind of like bistatic measurements of what is going on in the region, that region of the ionosphere. But I don't know whether that answers your question.
Sorry, I was muted. Yeah, certainly. I'm familiar with the HARP and SuperDarn experiments, or not closely, but I know they do. I guess I just wonder if that would work any with the wave, the waves that you see here, if they're.
Oh yeah, so yeah, it's just because we're running out of time. We actually we've done experiments where we've actually squinted the beam, right? And again, so over here, if you like, over the top represents emissions around the pump wave frequency, and the lower panel represents emissions around twice the pump wave frequency. And you can see that we get like multiple lines, and these lines are signatures of a decay process which involves electron and ion Bernstein waves, and we can see them at like near both the pump wave frequency and twice the pump wave frequency, and it's clearer over here. So again, you can, for HAP, you can tilt the beam to up to like 30 degrees from like the vertical. So I mean, there are lots of like a whole lot lots of range of experiments that you can perform. It just depends on how far away you are willing to travel from HAP to set up a remote station, and whether I mean, you would actually have electricity or whatever, like, because HAP is almost in the middle of nowhere. But I mean,
Yeah,
there's,
certainly.
yeah.
Okay, it sounds good.
Yeah, okay.
Yeah, we got started a little bit late, so maybe we have time for one or two more questions here.
And I forgot to mention, so I mean, we've performed experiments where we actually calculated the trajectory of, like, say, a GPS satellite, right? And we pumped, like, we directed the HAP beam, like, try to follow, like, in as much as it could, like the satellite. So the purpose of this experiment was to try to see like whether we could like induce scintillations in the GPS signal, right? So there are just whole lots of experiments that you can write a proposal to perform at HAP, and the bigger question would be, I mean, if you are trying to source for support for it, like what's the broader contribution of your experiment to like the field of space aeronomy? So yeah, several always opportunities to design and perform experiments.
Yeah, very, very cool. Well, thank you very much. Or I guess I should say, is there any one last question there? Otherwise, yeah, thank you, Augustine.
Okay,
Hopefully-
thank you. Yeah.
Thank you, everybody, for joining. And we will have another seminar next week from Dr. Lenny Smith. I should mention, I think I missed this before. He's a recent VT hire, so he is just coming in and navigating the world of getting adjusted to Blacksburg and Virginia Tech, all within this pandemic. So it'll be very good to hear from him. I believe next week. I need to make sure from that. I believe we'll have one next week. So, thanks everybody, and we'll
Okay.
talk to you next week.
Okay, yeah. Bye.